Dominant mode, dominant transverse electric mode in rectangular waveguide. By dominant mode, we mean that the mode which has the lowest cutoff frequency. As we mentioned, this is the field distribution of transverse electric modes inside rectangular waveguide, and from this field distribution we obtain the cutoff wave number Kc, and from the cutoff wave number we could obtain the cutoff frequency for the mode Mn. And we have seen that the cutoff frequency for the mode Mn equals 1 over 2 by square root mu epsilon square root m pi over a squared plus n pi over b squared. And we mentioned that the value of m and n can be 0, 1, 2, 3, and 4. However, the value of m and n cannot be 0 simultaneously. So the lowest modes that can operate or that can propagate in rectangular waveguide for the TE mode are M10, 10 mode or 01 mode. But we cannot expect that there is 00 mode, because 00 mode would correspond to transverse field component equals 0, which means that there is no fields inside the waveguide. So assuming that the value of A is greater than B, or in other words, A is the length of the waveguide and B is the width of the waveguide, so the lowest cutoff frequency in this case occurs when M equals 1 and N equals 0, or means that the mode TE10 mode, and once again is read as 10, not 10, because 1 corresponds to the value of M and 0 corresponds to the value of N. So the lowest cutoff frequency for the TE mode in rectangular waveguide would be F cutoff 10 mode, which would be 1 over 2 pi square root mu epsilon square root 1 pi over A squared plus 0. So this would be pi over A, and this pi can be eliminated with this pi. We can say that the cutoff frequency of 10 mode is 1 over 2A square root mu epsilon. And it should be noted that there is no transverse electric 00 mode. This means that for rectangular waveguide, the lowest frequency that can propagate inside the waveguide is given by this value. Or in other words, the rectangular waveguide for TE mode can correspond to a high pass filter which has a cutoff frequency equals 1 over 2A square root mu epsilon. So below this frequency there is no propagating mode. Below this frequency there is no power that can be transferred through the rectangular waveguide. So this is the lowest frequency that can be used to transfer power from one point to another point inside a rectangular waveguide. In this case, the field components for the dominant mode, which is TE10 mode, is given by applying M equal 1 and N equal 0. So in this case, here M equal 1 and N equal 0 will correspond to Hz equal A10 cosine by x over A, cosine 0, which is unity here, e to the power minus j beta z. And in this case, Ex and Hy are 0, and Ey and Hx would be minus j omega mu pi over A kc squared, and should be noted here, kc squared in this case would be pi over A squared. So this pi over A and this pi over A squared can be eliminated to kc. A10 sine by x over a, e to the power minus g beta z. So in this case, ey would be minus j omega mu pi over a, which is 1 over kc, a10 sine pi x over a, e to the power minus g beta z. In a similar way, hx here pi over a and here pi over a squared. So this would be a over pi, j beta a over pi, a10 sine pi x over a, e to the power minus g beta z. hx j beta a over pi, a10 sine pi x over a, e to the power minus j beta z. And exhy will be 0 and ez is 0 because I'm talking about transverse electric modes. So these are the field components of the dominant mode TE10 mode. And Kc in this case would be y over a, beta would equal square root k squared minus y over a squared, right? If I'm talking about the bar transfer for the dominant TE10 mode in rectangular waveguide, the bar transfer B10 is half the real of the integration E cross H conjugate. And if I'm talking about the propagating power along the Z direction, so the pointing vector in Z direction, so E cross H conjugate, all of this value dot Z, and the cross section area where the power is transferred is the cross section of the waveguide, so this dx dy, where x is from 0 to a and y from 0 to b. Now E cross H conjugate would be EY cross HX conjugate. Here minus J, and the conjugate here it would be minus J2. So minus J it would be minus 1 omega mu beta a squared over pi squared a1 squared sine squared by x over a, and here e to the power minus j beta z multiplied by e to the power plus j beta z, because the conjugate be unity. So the all these parts together would be omega mu a squared over pi squared, and here we have 2 a1 squared 10 squared real beta, and the integration of sine squared by x over a dx dy. The integration with respect to y, it would be directly b. The integration of sine squared by x over a, it would be a over 2. So this would be a multiplied by b over 2. So we have a squared already, it would be a cubed, b over 2, and we already have 2, it would be 4, but real beta. So if beta is real, the power will be transferred. If beta is imaginary, the power will be stopped. So in other words, beta here is the square root k squared minus kc squared. If k is greater than kc squared, beta would be real and the power will be transferred. If k is smaller than kc squared or below the cutoff frequency, beta will be imaginary and the power will be 0. So this is the power transfer through the rectangular waveguide for the dominant TE10 mode. It is omega mu a cubed multiplied by the magnitude of the electric field or the magnetic field, which is at a10 squared b over 4 pi squared real beta. Okay. For the conductor loss at the transverse electric 10 mode, the conductor loss will be proportional to the surface resistance multiplied by the current squared, and the square value of the current is proportional to the square tangential magnetic field. Effectively, for the plane y equals 0 and y equal b, the tangential field component are Hz, which is already we have, and hx. hx is tangential in this case. So in the plate y equals 0 and y equal b, we have two components. Component proportional to hz squared and another component proportional to hx squared. On the other hand, for the plate x equals 0 and x equal a, we have tangential magnetic field hz, but we don't have hy. So in these two plates we have hz only. So the power losses equal the surface resistance over 2 multiplied by the contour integration of the surface current J surface squared dl. The surface current is proportional to the tangential magnetic field, and the tangential magnetic field in the two planes x equals 0 are hz, where am I? Yeah, at x equals 0, at x equals 0 and x equal a are hz. So the surface current here, J surface, equals the normal component cross the magnetic field at x equals 0. The normal component is x. The magnetic field is hz. So the surface current here in the y direction and its magnitude is proportional to the value of hz at x equals 0. At x equals 0, the value of hz equals a10 cosine 0, it would be a10. Now, if I'm talking about the plane y equals 0, which is the bottom wall, J surface would be the normal, which is y, cross the magnetic field. The magnetic field here, we have two magnetic field components, hx in x direction plus hz in z direction. Y cross x would be in z direction and y cross z would be in x direction. Okay, so the surface current in the bottom wall would be the magnitude of the magnetic field hx at y equals 0. hx at y equals 0 actually is independent on y. So it is j beta a over y a01 sine pi x e to the power minus j beta z plus x hz at y equals 0. So this would be a10 cosine pi x over a. So this is the surface current at this side wall and this is the surface current at this wall. In a similar way, we can obtain the surface current in this side wall and on the top wall. Alright? Now, the power losses is the surface resistance over 2 integration of J surface squared, the magnitude of J surface squared dl. So the magnitude of J surface at x equals 0 is a10, and the magnitude of J surface squared at y equals 0 is beta a over pi squared multiplied by a10 squared multiplied by sine squared y x over a plus a10 squared cosine squared y x over a. This is the magnitude squared. When I'm talking about the magnitude, it means that this would be multiplied by its conjugate, so it would be unity, and I'm talking about the z component squared plus the x component squared. So in this case, the power losses due to the side or the left side and the bottom side would be R surface over 2 J surface square, J surface 1 square, J surface 2 square. Okay? And effectively, the top side and the right side are the same as the left and the bottom. So we are going to multiply this by 2. So the power losses would be R surface, the integration over Y from 0 to B, multiplied by the surface current at the left wall square, which is J surface Y square. This is J surface Y square, which is the amplitude A10 square. Okay, dy. So this is simply R surface B multiplied by A10 square plus the power losses in the lower bottom multiplied by 2 because this is similar to the upper bottom. So R surface integration over X from 0 to A, J surface in X direction squared, which is A squared cosine squared by X over A, plus J surface in Z direction, which is beta A over pi squared, A10 squared sine squared by X over A. Okay? Effectively, cosine squared by X over A and sine squared by X over A, by integrating over dx from 0 to A, it would be A over 2. So, in this case, the second integration would be R surface multiplied by A1 squared. Here we have A over 2 multiplied by B, A over 2, no, A over 2 only, A over 2 without multiplying B, A over 2, this corresponds to this term, and the other term it would be A over 2 multiplied by beta squared A squared over pi squared, so it would be beta squared A cubed over pi squared. This actually was beta squared A squared over pi squared multiplied by A over 2. So A multiplied by A squared would be A cubed, and this is 2. So this is the power losses for the TE10 mode, or this is a conductor loss for the TE10 mode. Now from the conductor loss, power losses, and previously we have obtained the transmitted power B10. Now by dividing power losses over 2B10, we can obtain the attenuation coefficient due to the conductor loss. The attenuation coefficient due to the conductor loss of TE10 mode in rectangular waveguide is power losses over 2B10 mode. Power losses, we have obtained this formula for power losses, and the transmitted power B10 mode we have obtained previously this equation for the transmitted power. So by dividing this by this and dividing by 2, we obtain the attenuation coefficient due to the conductor loss, in this case power losses over 2B10 mode. From this it would be R surface A1 squared, and already we have A1 squared in the denominator, it would be eliminated here. R surface multiplied by B plus A over 2 plus beta squared A cube over 2 pi squared. Now here we have omega mu A cubed beta B multiplied by beta, and we have 4 pi squared here, so it would be 4 pi squared, and already we have division by 2, so this would be 2 pi squared. Now by arranging this formula, we can say that omega mu can be replaced by k eta. K eta. A cube b beta and surface resistance, and already we have 2 pi squared here. So this 2 pi squared b plus beta squared a cube plus 2 pi squared a over 2. And we know that pi over a is k. So pi over a, pi over a is kc, not k. We can arrange it like this. I'm not sure. Okay. Anyhow, this is some algebraic simplification. I'm not sure about it right now. Okay. This is the attenuation coefficient due to the conductor loss of the TE10. Alright? Okay.